Hello, everyone. So in this lecture, we'll be talking about the frequency distribution of data collected at a statistical experiment. And we are going to also be talking about some graphs or some pictorial representations of your data or the frequencies of your data. Okay, well, let's get started. We are learn today to construct a frequency distribution, which is a very easy thing to do. You will see through that through some examples. And to represent this in a graph, we can use histograms, frequency polygons, or stem and leaf, or even a pie chart, or sometimes they call them circle graphs or pie charts. It's the same thing. So a piece of data is a single response to an experiment. It could be, for example, the age of an employee, could be the salary of a family or income of family, or anything, just when you are dealing with just a single response. A frequency distribution, however, is a listing or a list of observed values of what you collected. But I don't know how to say, it's just like when you count, and you will see this very easily in 3 examples. And then for each piece of data, for each piece of data you collect, then you are going to count how many times that piece of the data occurred or is occurring in your distribution. And how many times it occurs that's what we call the frequency of that piece of data. Well, here is, suppose that you are interested in studying the number of children per families, and then you surveyed or you talked to 64 families and you get this table. For example, 1, 2, 3, 4, 5, 6, 7, 8 families, they have no kids among those 64 families and so forth. 9, 10, 11, you have 11 families with only 1 child, and then you get my point. And also we have here 1 family with 9 kids. So the frequency table should something look like this. For example, how many families with no kids? We have 8 of them. How many families with 1 kid? We have 11 of them, and so forth. How many families with 9 kids? We have only 1 family. Well, we have only 1 family among the 64 families that we talked about. And that's what we call the sample. And we talked about sample in previous lecture. So how did we come out with those 64 families? Well, we used a sampling technique, probably stratified or cluster or systematic or something like that. But now that we have the families, 64 families, this is the data of those 64 families. Well, we just said that. So the total is 64, 8 families with no kids, 11 families with 1 kid, and so forth. So sometimes if the collected data is too much, so we may group the data into classes, and each class or each group should be of the same size, the same, sometimes called the width. And of course, we should not have any overlapping between the classes, otherwise we'll be counting things more than once. And of course, each piece of data should belong to only 1 class, and that's obvious, I guess. Well, they often suggest that we use between 5 to 12 classes but I'm not too excited about the last sentence here. It depends on the size of the statistics project you're dealing with. So, but if you have to choose, maybe you can choose 5 to 12 classes. Here's an example. For example, you have a first class between 0 and 4. I'm not referring to the previous example. This is just a random example here. So those are the lower limits, 0, 5, 10, 15, 20, 25. And the upper limits are 4, 9, 14, 19, 24, and 29. So as you can see here, so 0 to 4, so the size of this one here is 5. So we have 5. And also from 5 to 9, we have the width of it is 5 and so forth. And for each class, you may talk, the midpoint of each class is found by adding the lower to the upper and divide everything by 2. So 0 plus 4, which is 4 divided by 2 is 2. So the midpoint of the first class is 2. The mid class, let's see, for this one here is 10 plus 14, 24. 24 divided by 2 is what? Is 12. So 12 is the midpoint of this class. Here's another example. So suppose that the following set of data represents the family income. These are in thousands of dollars, rounded to the nearest hundred. Those are 15 randomly selected families. Well, randomly, again, someone may question this. Well, how randomly? But anyways, that's not the concern of today's discussion here. So we have 46.5 thousand, 31.8 thousand, and so forth. Those are the incomes, the 15 incomes of those 15 families. So the question says here, construct a frequency distribution with a first class between 31.5 to 37.6. Well, it does not mean that 31.5 is actually one of the salaries, nor 37.6 is one of the families. So the width or how to decide your class, it depends on your data. Of course, you don't want to pick a very large class, a very small class. If you take very small class, you end up with defeating the purpose of this classification technique. So here it happens that 31.5 is earned. What is it? 31.5? Is it? Maybe it's not earned at all. We don't have 31.5 here at all, but that's fine. So here we have 31.5 and 37.6. We are going to, so this is the first class. What's going to be the second class is 31.7. So we are going to, so how can we do this? Of course, we're going to go back to those numbers and we need to rearrange them, sort them from smallest to largest. It will make your life easier. Earlier, I wanted to see what is 31.5, but I couldn't see it, but I had to really work hard on it or make my eyes work hard. But if the data was sorted, it would be much easier to detect whether that was one of the incomes or not. So you sort the data. Here it is the data, 31.8, 40, 44, 48, and so forth. So how many salaries fit into this category? Well, we have one, which is 31.8, right? Oh no, I have actually two. And 35.5. So these two belong to the first class. So we have, like I told you, the first class has two families in it. And we need, the width is 6.2. So the width of this class, 37.6 minus 31.5 is 6.2. So we make sure that the next class will have also width 6.2. The width of it is 6.2. So how they construct the second class? What's the number that comes right after 37.6 is 37.7. Add to that 6.2, you get 43.8. And then 43.9 plus 6.2 gets you 50. And so forth. So how many families in this class? We have two of them. How many families in this class? You have three of them. Well, how could I tell? Well, just look back again and just see which of these numbers fit between 37.7 and 43.8, and you find out three of them. Again, how many families we have? We have 15. The last class here, as you can see, we have only one family that earned between 62.5 and 68.6. And that family is 65.2. Again, the endpoints of each class are not necessarily occurring in the data, nor the midpoint, nor any point. So where the class starts and ends, it depends on you. Or the exercise will tell you, well, we want to construct classes starting at this value and at that value. So if I give you only one class and where it starts, I can construct the remaining classes. So the model class here, the model class is the class that occurs the most, which is this one here. This is called the model class. Or the mode in general in statistics means the piece of data that is occurring the most. So the class or the number, the max or the highest number of families belonging to these classes is the one that between 43.9 and 50. That's what they call the model class. And the class mark of the first class is, well, the middle point, sometimes called the class mark, or the midpoint, is 34.55. You can do the class mark of this one here, of the model class, or any class. Just add the endpoints and divide by, add the end values, divide by 2. Now that we have data and we know how to create a frequency table, sometimes it is very useful to represent things pictorially in a picture, in a graph. And one of the graphs are histograms. So a histogram is just a graph with observed values on its horizontal scale and the frequency on the vertical scale. So, well, the histograms are sometimes called bar graphs, are easy to read. That's why you find them in newspapers and magazines, or when you watch news. So are very common graphs to use for the general public. Well, how do you construct a graph? It's really easy. So I'll go straight to the point here. So let's go back to this frequency table. So by the way, you can construct a histogram using data directly or using classes. If you convert this to a frequency of the classes, that's fine too. So here you can create one bar for the families with 0 kids, one bar for the families with 1 kids, and one bar for the families of 12 kids, and you obtain something like this. So how many people or how many families having no kids? It's 8, right? Here is 8. How many families having 1 kid is what? Is 11. So now the width that you can put here is up to you, really. So the scale on the horizontal, it's irrelevant. You just make sure that every bar has the same width. So that's how it goes. And of course, here, this is the frequency or the number of families that you are studying. And actually, the histogram will give you an idea about how the data is distributed. Right? Here, somewhat centered, kind of like, or it tells you that the mode here is 2, means that the number of kids or the largest or the highest number of families are the families with 2 kids. You can represent the same data of this table using what's called a polygon or frequency polygon. Let me go straight to the example here, so you can see, or to the representation, or the example. We go back to the same example we had. We can have what's called, this is number of children per family. Same thing that we represented with histograms. Now we are representing with this polygon. The word polygon means it's just like segments, right? So this number of families. This starting, I might not agree with this portion here, but again, so it's probably they do it. Same thing at the end here. So I would stay with this dot, not including this portion here, nor including the last one. So how many people with 0 families? You have 8. You just put the dot there. How many people with 1 family? How many families with 1 kid? You have 11. Put a dot there. How many families with 2 kids? You put dot there, and so forth. And just join those dots by straight lines or straight segments. And there you have what's called a polygon representation. It turns out that you can represent things using what's called a stem and leaf display. A stem and leaf display is a tool. The good thing about this tool is that it actually shows you the collected data on the graph. So you will see the actual values that makes the data. I'll give you an example because sometimes explaining example will fulfill the learning goal. So instead of just talking too much and making you confused, let me go straight to the data or to the example, and you will see how to construct a stem and leaf chart or graph. So suppose that the table below indicates the ages of a sample of 20 guests who stayed in a certain hotel. It says construct a stem and leaf display. If they don't say anything else, so for example, you have one person, 29 years old and 31 years old and 39 years old and so forth. All these people are 20 people who visited this Captain Fairfield Inn bed and breakfast. So mostly use the digit of the tens as your stem and the rest is the leaf. For example, 29, we have another 20 something, 28, we have 2 people in the 20s. So what we're going to do here, we're going to put how many people in the 20s, the 30s, the 40s, 50s, and 60s, and 70s. If let's see, we don't have anybody in the 50s, just don't include it. Or just put 5 and don't put anything on the leaves region. Oh, actually, we have 3 people on the 20s. I count only 2. This is 20. That's why it's always a good idea to sort the data so you don't miss anything. So I see 29, 28. What is the other one? Oh, here it is, 27. So we have 3 people. That's right. So we have 29, 27, 28. And then we'll do the same thing for the 30s. We have 31 years old, we have a 39 years old, and 32 years old. As you can see here, you don't have to sort the leaves. Yeah, but I find it convenient if you sort them. Instead of 9, 7, 8, you put 7, 8, 9, you put 1, 2, 9. But again, it's not a requirement. And this is called a stem and leaves or stem and leaf display. So like you say, it gives you, you can see here, if you look at it, I don't know, not upside down, but it's just like sidewise. It's like in distribution. You have more people in the 40s visiting that hotel. So if you have to do a classes here, for example, if you want to convert this to classes, for example, from the 20s to the 30s and from the 30s to 40s and so forth, from, let's say, from 20 years old to 29 years old, from 30 years old to 39 years old, from 40 years old to 49, and so forth. So you will see that this is the model class, and this is the mode right here. Pie chart, sometimes called circle graphs, are often used to compare parts of one or more components of the whole to the whole. So you wanna just fit, you wanna have like a portion of the graph compared with the whole graph. Here's an example: favorite performance at the circuit. For example, I say 38 people love tigers in a circus. 26 people, excuse me, they liked the elephants, and acrobats 17%, jugglers and 14% out of 5%. This is just another way to represent data. Well, here it does not tell you how many people were surveyed, right? And also we need to point out that it's something that should tell you that, well, this survey, for example, they told people, just give me one thing that you liked. For example, you don't have a person who liked acrobats and at the same time tigers. So if you have this situation, then given the number of people who participate in the survey, I can tell you how many people or spectators that are actually the ones who like tigers. Suppose that we have 800 people. This is actually good. So 800 people. So that's the number of people that we surveyed. So tigers, the 8%, well, just multiply the 8% times 800. And you get the number of people liking tigers in the following table. So tigers, you got 38%, which is 0.38. 0.38 times 800 is 304. So we have 304 people like tigers. We do the same thing for the other categories: elephants, acrobats, jugglers, and so forth. And if you add up all these numbers, of course, you have 800. That's why I said we don't have overlapping. We don't have people counted twice. If so, then we cannot do this. So, well, this is a solution, really. So if you were asked, given that we have 800 people participating in this survey, how many of them, and given that pie chart, how many of them like tigers? Well, that's 304. 136 for acrobats and 112 people like jugglers and so forth. Well, I hope that you understood this lecture. It's pretty straightforward. If you don't understand something, please let me know. Okay, well, you can go now and start your homework, 12.2.